Hi students, welcome to one more video on electronic circuits. So we were discussing prerequisites for analog electronic circuits. So in this video we'll see how to use Laplace transforms in circuits. Before we actually start the real stuff, okay, you just have a look at these slides. So before we begin, you should be knowing electrical or electronic circuits. So you should have a concept of Kirchhoff voltage law, Kirchhoff current law, and you should be knowing the very basic Laplace transforms, and you should be start off using scientific calculator. Of course, so you should have a notebook. Of course, use pens of different colors so that you can understand the things comfortably. Of course, you need to apply your mind, brain, make sure that turn off all your disturbances. So of course this is very much required, so you need to set aside quality time for this. Write down everything, make sure that you give your best to understand the concepts. Okay, so we shall proceed. Yeah, maybe in the earlier videos you might have seen we have actually solved the problems of AEC prerequisite task number 2. One of the task was this. One of the task was you had a capacitor, and then I did ask you to find the value of V0, and then of course this is another circuit where the resistor capacitors are interchanged, and again we are asked to find the value of V0 for a given frequency. And then in this we actually asked at what frequency output voltage is input by √2. Again over here you might have seen, okay, it was a lengthy process, and of course we could able to solve it using this method also, and this is what we got. And of course you might have seen we've actually done the the solution of that. There was a video on which we replaced, okay, we considered this as a complex quantity, the reactance of capacitor, and then did so many things, and we could able to prove that, okay, what all values we got is okay. You are somehow convinced, and you all felt, okay, oh, it's a very lengthy process and all those stuff. Now let us see now. Let us take the same circuit and try to use this Laplace transform. Now how best you can the use of Laplace transform in electronic circuits where it is having various passive components, how does that simplification becomes very easy. The solution can be easily found with the use of Laplace transform. So we know that Laplace transform of any integral is given by f of s by s. Again, Laplace transform of any derivative will be given by s into f of s minus f of 0, where f of 0 corresponds to the initial condition. If you consider initial condition is not there, then you can treat it as 0, meaning Laplace of an integral is f of s by s. Laplace of a derivative is s into f of s. So using these two Laplace transform, let us try to solve the same old circuits what we discussed earlier, which is having a resistor and a capacitor. So when I take, now this is, you have a resistor and a capacitor. Assume that this is V, and this is I naught. let us proceed. So we have an RC network. So let us assume that there is a current IFT flowing through this. So these are all with respect to time. So we can actually write a KVL for this, where V of t, the applied voltage, is nothing but resistance into the current, that is I of t plus, and we know that whenever you have a capacitor, voltage drop across that capacitor is 1 over C integral of I dt. So this is what is the expression for this is the KVL expression for this loop. So where V of t is given by R into I of t plus 1 over C, so on so. So what is V naught of t? V naught of t is nothing but this drop, that is 1 over C integral of it dt. This is what we have. So now let us use the Laplace transform to write the Laplace transform of these two equations. So equation 1 and equation 2. So what does the equation 1 says? So you have, suppose now what I'll do, Laplace of V of t is equal to Laplace of R I of t and Laplace of plus Laplace of 1 over C integral it dt. So this is what is Laplace. So we know that Laplace of V of t is nothing but, okay, this is rated as V in. So now it is V in of S. So this is my Laplace. So this is V in of S is my input. So it is Laplace of R. Of course, this is a constant. So this is R. So this I will become IFS. So what is this? So this is again a constant. This is 1 over C. Now you can see it is integral of IT into dt. I of t into dt. So now as we know that whenever you have an integral Laplace, it is IFS divided by S. So the Laplace of this first equation comes out to be something like this, so that I can write this as, I can take IFS as common factor. So IFS to R plus 1 over SC. So this is my V in of S. So shall I write it as V in of S? Then what is the Laplace of second equation? It is Laplace of V naught of t equals Laplace of 1 over C integral I of t dt. So then what is Laplace of this? Laplace of this is V naught of S. Now you can see again Laplace of 1 over C remains constant, which is a constant, so that remains as it is. Now it is integral of it dt. So this will become S, okay, this will become IFS by S. So now can I write this as V naught of S is equal to IFS divided by S into C. So I have two equations, two Laplace transform equations from this time domain equation. So let me use these equations and try to find what is V naught of S. So now can I write I have V naught of S as equal to IFS by S into C, and I have V in of S as equal to what I have. So I have IFS divided by IFS, that's what, okay. So V in of S is actually IFS multiplied by R plus 1 over SC. So from this, can I write IFS as equal to V in of S by R plus 1 over SC? So now I can write this. So in this expression, shall I replace this I naught? So what I'll do, I will replace this I naught by this quantity, So what is this now? V naught of S. V naught of S is V in of S divided by R plus 1 over SC multiplied by SC. So now what happens to this? So what is the final expression? You multiply this with this. So what is V naught of S is equal to, it is V in of S by, if you multiply this, is it not becoming, okay, SRC plus 1? Or can I write V naught of S by V in of S as equal to 1 plus SRC plus 1. So now this is the Laplace transform of V naught of S by V in of S, which is now 1 over SRC plus 1. 1 over SRC plus 1. So now how this is useful in finding these values? You can see we had this circuit. Can you see we had this circuit? So this is this, exactly we have this. So now how does this is useful? Okay, you had a input of 9.99 times V in when the frequency is 1000, when the frequency is 1000. Let us try to find out this. So now what is the usefulness of this equation in my electronic analysis? Now for our electronic analysis, we replace S by j omega. S by j omega. When you replace S by j omega, so what is this? V naught of S by V in of S will become 1 over j omega RC plus 1. Can you see now this has become, this is a j term, j omega RC plus 1, because you are replacing S by j omega. So when I replace this, can you see I have a complex quantity here? So now this ratio of output by input has got a complex quantity on the right hand side. So when you have a complex quantity, you're going to have a magnitude and a phase angle, So what is the magnitude of V naught of S, V naught of S by V in of S? It is nothing but 1 over, of course we know that when you have A plus JB as a complex term, so what is its magnitude? Is it not 1 over A square plus B square? What is its phase angle? Is it not tan inverse of coefficient of imaginary by coefficient of real number, real value? So what is this magnitude now? Magnitude is 1 over 1 plus omega RC whole square. This is the magnitude. How much is the phase? Phase is, of course it's actually 1 over tan inverse of omega RC by 1. So since it is 1 over so and so, can I write it as minus tan inverse of omega RC? So this is the phase. This is the phase. Now I have a magnitude, I have a phase. So when you have magnitude and phase, it's very easy to find what is the ratio of V naught by V in for a given frequency, So what is frequency? So we know that this omega is nothing but 2 pi f. So what you can do is, okay, we had this equation, no? we had this circuit, For this circuit, what was the, now you can substitute. So what is 2 pi f? So 2 pi f is actually 2 pi into f is 1000. How much is the value of R? R is 100 ohm. How much is C? C is 0.1 microfarad. So this is the value of this is 2 pi 1000, so on. So now do you have all the magnitudes, all the values of this omega RC to find the magnitude? So you can substitute that and you can actually find out. So how much is this? So magnitude becomes, so is it not under root of 1 plus, open the parenthesis, is it not 2 into pi into 1000 into 100 into 0.1 exponential minus 6 whole, okay, multiply square and then close it. It is this, and 1 over that is 0.998. Can you see this magnitude? The magnitude at f is equal to 1000. Is it not 0.998? That's what we had here. this is what is, okay, this is what you have, okay, and you have it as, this is 0.998 if you multiply with this 10, because you are actually looking at what is V naught. So now when you actually consider that exact value of V naught with a V in of 10, so then this becomes 10, it will become 9.98, which is very close to the value of this. This is 9.9. On the same lines, so we had one more circuit. So did we had this circuit here? Here, can you see here? How much is the value of R and C? So let us find out what are these values. So what is the value of R now? So let me just replace this by R is equal to 1 kilo ohm. What is the value of C? C is 10.1 microfarad. We are actually finding what is the frequency at which V naught by V in was root 2 or 1 over root 2. So when V naught by V in was 1 over root 2. So this is the condition. We are actually we are asked to find the value of F, so that this ratio is this. So how do we do here? So let me make this V naught by V in as 1 over root 2. Let us replace this by 2 pi f. R is equal to 1k, C is equal to 10.1 microfarad. Let us look for the value of f. So let me rewrite that. So see here, in that solution you might have seen we did lot of calculations and then we could able to find out this. Now we have this equation, equate this to, because it's the equation of, it's the relation of V naught by V in, which is equal to 1 over root 2, the condition given. We are asked to find the value of frequency at which output voltage is 1 over root 2 times the input, and we are asked to find the corresponding phase. Maybe in the simulation we found that phase is equal to minus 45 degree. Let us verify that also here. So let us verify that also here. So what we'll do now, so let me rewrite that equation. So what is the magnitude? Magnitude is 1 over root of 1 plus omega RC whole square. R is equal to 1 kilo ohm, C is equal to 10.1 microfarad. This is what V naught by V in. This ratio is equal to 1 over root 2. We are asked to find the value of F. Where is F? Where is actually F is there in 2 pi f. So what I'll do, I will write this as 1 over under root of 1 plus 2 pi f. How much is the value of R? This is 1k into 10.1 micro whole square, and this is 1 over root 2. So I'll make it as alpha A and then find it. So actually we got the answer as how much? 17.56 so and so. Let us find out. So I think if you can remember, it was a huge process of finding it. Now over here, using Laplace transform, you are getting the magnitude and phase equations immediately. So you have to simply plug in the values of R and C for a given requirement. Now the requirement is at what frequency this becomes 1 over root 2. In the previous case, we found for a particular frequency what is the ratio. So what I'll do now, it is root 2 1 over alpha equals, again it is, okay, I'll make it 1 over, I'll make it under root, okay, it is under root of 1 plus open the parenthesis 2 into so that will, let me redo it, under root of 2 inverse alpha equals, open the parenthesis, square root, open the parenthesis 1 plus, open the parenthesis 2 into pi into alpha a, because this is a unknown parameter, alpha a into 1 exponential 3 into 10.1 exponential minus 6, close the parenthesis, whole square, close the parenthesis again, and then one more closure, inverse of that, shift calculate. I should get 15.78. Oh, I got it. 15.75 hertz. Because you are looking for frequency, isn't it easy? So in order to get the same value, if you can just show you the calculations we did in the earlier videos, you can see we did all this stuff. You can see we did all this stuff with this as 10 point here. This is 10.11 micro, and then we did all this see here. See, we got all these things, and then we actually find out, okay, what is the value of this f as 15.75 hertz. So that is corresponding to V0 is equal to 1 over root here. That was such a lengthy process. Now we can see use of mathematical calculations in electronic circuit makes the life of an electronics engineer very comfortable. So that's why they are going always hand in hand. So we got the frequency as this. So now for this frequency we are asked to find the phase. Of course, we did the simulation. When we did the simulation, the phase was around minus 180 degree, minus 45 degree. Minus 45 degree. Let us see how much is the phase is. So now what is the phase? This is your phase equation. Can you see, this is your phase equation, minus tan inverse of omega RC. So how much is this? Is minus tan inverse of omega RC. So it is minus tan inverse of how much is omega? It is actually 2 into pi into 15.75 into what is R? R is actually, so R is 1K, C is 10.1 micro. So let me substitute all these things. It is actually minus tan inverse of 2 into pi into 15.75 into 1 exponential 3 into 10.1 exponential minus 6. Can you see it is minus 44.98 degrees? Can you see it is minus 45 degree? That's what we got it in the earlier calculation also. If you can remember, maybe in the simulation I showed the phase is coming out to be, let me show where it is. Okay, we actually substituted that and found out the phase here. Can you see it? It's minus 45 degree. So we did all these calculations. So this is exactly how a Laplace transform of a given circuit can be easily used to obtain the solution. So of course, in this also we took this circuit, wrote the time response, time domain equation, KVL, and then we applied the Laplace transform, all those stuff. That can be even further simplified. So let us see how do I even further simplify that. Let us take the same circuit, because for this circuit, which is a circuit I have this circuit. So this was the circuit what we used. This is R, this is C. If it is V0, if this is Vin, we got V0 of S by Vin of S as equal to 1 over SRC plus 1. So this is upon doing all those stuff. So now what I'll do is, I will write this circuit diagram in Laplace transform. So meaning this R remains R, this Vin of t, this V0 of t will become Vin of S. So this will become V0 of S. Now this C becomes 1 over SC. Correct? Now this is the Laplace of C. This is the Laplace of C. This is in Laplace form now. This is IFS. This is IFS. What is V0 of S now? V0 of S is IFS multiplied by the impedance. What is the impedance? It is 1 over SC multiplied by 1 over SC. What is IFS? IFS is input divided by the overall impedance. So it is Vin of S divided by, what is overall impedance? It is R plus this 1 over SC is IFS. So shall I now replace this IFS by this quantity? Is it not? Vin of S by R plus 1 over SC is your IFS multiplied by 1 over SC. Take the LCM. So when I take the LCM, this will become Vin of S it is SRC plus 1 by SC. This is 1 over SC. This will go off, so you'll end up with V naught of S by V in of S as 1 over 1 plus SRC. As simple as that. See, we even didn't write the time domain KVL. We could able to directly write the KVL. Of course, V naught is nothing but current flowing through this multiplied by the impedance. Impedance of this is 1 over SC. What is the impedance of this? This is R. What is the overall impedance? It is this plus this. So that's what is this. So in this loop, you have a voltage V in. What is the overall resistance of the loop? It is overall impedance. It is R plus this impedance. This impedance is 1 over SC. So likewise, when you are writing its Laplace transform of the circuit, it becomes further easy to, because if you have this, then you can write the magnitude equation, phase equation, then you substitute the required condition, you'll get either the frequency or the output voltage at a given frequency or whatever the condition is. Now let us move to one more combination where you have a capacitor first, resistor. If I have this is V naught, this is V in. Let me write it as its Laplace only directly. So this is R. What is this? This is 1 over SC. This is IFS. Correct? So what is V naught of S? V naught of S is current flowing through that resistor multiplied by the resistance. That's what is your Ohm's law says. Ohm's law says the output voltage across resistor is nothing but this voltage, which is nothing but current flowing through this multiplied by resistance. But what is total current flowing? So IFS is the input voltage V in of S and overall resistance of the loop. So it is this resistance or this impedance which is of capacitor. This is R. Take the LCM for this. Will it not become V in of S? So this SC will go up as well as 1 over SRC. Correct? So this is what is IFS. Then what is V naught of S? In place of IFS, I'll write this. V in of S into SC by 1 plus SRC. What is this? This is again R. So what is this now? V naught of S by V in of S. It is SRC by 1 plus SRC. As simple as that. It is SRC by 1 plus SRC. What is the magnitude? Magnitude is, okay, when I say V naught of S by V in of S, magnitude is, of course you have to replace S by J omega. When you are replacing this by S by J omega, does the equation become J omega RC by 1 plus J omega RC? What is the magnitude of this? What is the magnitude of this? So magnitude of this is the square root of omega RC whole square. Then this square root and this square will go. So you will have magnitude as omega RC in the numerator. What is in the denominator? The denominator you have it as 1 plus omega RC whole square under root. This is the magnitude. How about the phase? What is the phase of this? So phase of this is, because you have like, okay, tan inverse of omega RC by 0, because this is actually plus 0. When you have something 0 in the denominator, this becomes infinite. What is tan inverse of infinity? It is 90 degree. So phase is 90 degree corresponding to this term. What is the phase due to this term? Phase due to this term is actually tan inverse of omega RC by 1. Since it's the denominator, when you take it to numerator, that will become minus tan inverse of omega RC. So this is the phase. This is the phase. So for any circuit for that matter, whenever you have a sinusoidal signal, it will have a magnitude and phase. Maybe you might have seen in the previous solutions of AEC pre, there was a sine wave of some amplitude at the input, and at the output amplitude was reduced. Not only the amplitude, the phase was also, it was leading or lagging. can see it was actually going like this sometime, or it was going like this sometime. So this was phase lead, this was phase lag. So that's what is this says. So when omega, when you have some angle, you can see the phase becomes positive. In the previous case, the phase was negative. The phase was negative. So because it is always minus tan inverse. You can see that? This is minus tan inverse of so and so. The phase is always lagging. So this type of circuit will always end up with a phase lead, whereas the other type of circuit will always have a phase lag. Okay, these are very interesting things that are lined up in electronics, especially use of mathematical solutions onto electronic circuit will make your analysis of the circuit very easy. Especially the Laplace transform is one of the fundamental concept, will be extensively used in electronic circuits to analyze the circuit. So without Laplace, it is so difficult to analyze the circuit. Thank you.